This video here is going to be about this little setup we have here. A bit of a closer look. You'll have to forgive my voice because I have the flu and it's damn near the middle of summer here, which is normal. Okay, we don't really require a schematic for this setup. We simply have an AC capacitor, a 265 ohm resistor and two plain Jane neon bulbs, 110 volts, hooked in series. Doesn't matter which way around they go, doesn't matter which way around the resistor goes, or for that fact the capacitor. I took the liberty of breaking one of the neons apart, and as you can see, I hope you can see, I'll try and get it focused. It is just two metal probes. So they are a linear globe, and of course so is our resistor and also our AC capacitor. So just before we go any further, a couple of other projects. Now I have these two here, and one actually sits horizontal and the other one sits vertical. If we can see that. This camera doesn't do a very good job of focusing, so we're not going to be able to see it by the look of it. The light's a bit of a pain as well. Oh, upside down perhaps. Can't even see it myself. So anyhow, that's for one of our projects that we're up to speed with at the moment, and it's underway. Also have now gone and bought myself 2000 watts of halogen globes, 500 watts, 2 in each pack. As you can see, 500 watts each. So we have 2000 watts of halogen globes ready to go onto our induction cooker experiments. See how that goes. But anyway, back to this. Okay, so we know how that's set up, and I'm simply using a small bit of wood here, so as the metal frame of our soldering clamp is not touching the unit in any way. And here I just put two spade connectors, one red and one blue. The red of course is the positive side, which is hooked onto the side of the capacitor the resistor is on, and the other is our negative. Here I have a 12 microfarad AC cap, 350 volts, blah blah blah. I've marked one side with a white line, and this is purely so we can swap the leads over. And what we're going to do is start the unit up, and we're going to fill that cap full of a voltage without our meter hooked up, just to eliminate any doubt that that could be doing something within the system. Okay, so we will get this thing up and running. Our lights are shining. Now I have it set in the position where we achieve the most voltage from the unit. Now to make sure our cap is discharged, I'm going to call the white line the negative side, and we will be hooking our meter up the same way each time, but we will be swapping the leads over, and we're not even going to discharge the cap when we do that. We'll just simply leave the charge in it, swap the leads over and let it charge back the other way. We are set on ohms, which we don't want. Now we are on DC volts. And I would say, having it set on the ohms, I might have put a little bit of charge into it. So that's how it reads resistance. So discharge that. Okay, so So we've got 0.1 of a millivolt, so I think that's pretty flat. So we are going to disconnect our meter. Now I am doing the camera work by hand, so I will try and keep it steady, but this was just so we could see step by step what's happening. So first we'll plug the positive output of this unit, which is supposed to be linear, and the negative onto the right side. And like I said, our meter isn't hooked up at the moment. As you can see, that cap there is simply hooked to this cap here. So once again, that's just to eliminate the meter from the system, so as we know that that's got nothing to do with what's going on here. Okay, so we should have enough in there now. It is only 12 microfarads. We'll disconnect that, and we will put our negative on the side with the right stripe, positive there. That is the voltage in our cap. Okay, so the voltage is slowly bleeding down. It's only, like I said, a 12 microfarad cap. But we won't discharge it, we'll let the system do it itself. So now we'll put terminals on the opposite sides. So red is going to go on what we call negative on this cap, and the blue one there. Now once that's charged up, I'll put the negative of our meter back on the same terminal and the positive on there, and all things being equal, we should get a negative voltage reading on our meter. So that should be enough, I hope. Put our positive back on there, negative back on there, and we have negative 15 volts. So we've eliminated the meter from the system. We've also shown the fact that the globes we are using, which I have many of, are indeed linear globes, and of course a resistor is also linear, along with an AC capacitor, as we just seen with that test there. What we're going to do now is we're going to hook our scope up to the outputs, and I will move the unit forwards and backwards, and we will watch the voltage go up and down on our scope. So of course our probe will go to our positive side, and if I can get this is awfully hard one-handed. And our ground will go to the negative side. We will zero the scope out. As you can see, it is zeroed out. And we have about 12-13 volts there, about 2.5 divisions, and we are set on 5 volts per division, and our probe is set at 1x. Time divisions don't matter at the moment, but they will shortly, because I will show you something else interesting. But what I'm going to do now is simply just move this backwards or away from the tower, and we can watch what happens. As you can see, our voltage goes down to 0, and there we go. The lights are out, 0 volts. As we move our unit back towards our tower, our volts once again start to climb. So just like that. Okay, so now we're going to add a little bit more confusion to the system. I'm going to place our probe across the resistor. Of course we'll have ground on that side and positive on this side, but in this case it's not going to matter. Okay, turn the volts to 1 volt per division and our frequency up to, what have we gone, 5 microseconds. We will zero our unit out once again, and there we go. A perfect AC sawtooth wave across the resistor, and yet we're getting a DC current out of the unit itself. And the same thing once again, moving it away or towards the tower, we can find our peak voltage, which is about there. So there you have it. I'll also switch it over to AC. As you can see, no change. Now it does change, of course, when I put my hand closer to the tower. So there's a little puzzle for you guys. We're getting a DC current out, but we have perfect AC across the resistor in the shape of a sawtooth waveform. So something for you to ponder over. Like I said, I do have a theory on this, but I'll wait and see what you guys come up with. Cheers from the Tin Man. Okay guys, just a bit of an add-on. I forgot, and I should have put this in the video, but like I said, with this flu, I'm not thinking too clearly. Once again, I have the probe in the ground across the resistor, and what we're going to do is just have a look at the scope so as we can see what voltage we have across that resistor and the frequency that we're operating at the moment. So the resistor is 265 ohms. It reads, or it measures to 65.7 ohms to be exact. Our scope at the moment is set on 1 volt per division, and our time scale is set on 2 microseconds per division. Our peak to peak voltage across that resistor is about 3.2 volts. Well, 3.2 divisions, so that's 3.2 volts across that resistor. And our frequency, we have 2 divisions per cycle. So at, of course, 2 microseconds. So you'll be able to work out the frequency and the current going across that resistor. So I just thought I'd throw that on there. Now the other thing we're going to look at is we need to eliminate the fact that the scope may also somehow be rectifying the current. So once again, this is awfully hard with these things, we will hook our scope back up the way we had it before, get back to our 5 volt divisions, make sure it's zeroed out, turn our time scale down a bit, we don't need it up that high. Okay, so as before, you've seen, I'll try and get this in the shot, that when we move the neons away from the tower, the voltage goes down and up. What we're going to do now is simply swap the ground, if I can get it off, and the probe with the negative and the positive, to eliminate the fact that the scope itself could be somehow rectifying the current. Okay, now you will see, we will zero it out again, we're still at 0. Now you'll see we have about 12 volts in the opposite direction. Once again, if I move the lights away, we can see our voltage goes to 0. And as we move our lights closer to the tower, we're getting a negative voltage. So that eliminates the scope as well as doing any sort of rectifying within the circuit. So I don't think there's much more we can do to eliminate bits and pieces from the circuit that could be doing the rectifying. So I think I might call this TinMans linear rectifier circuit. We've got to put our name to something, unless of course someone else has found this effect. Okay, well that's it for me. I'll go and get this video joined, edited and uploaded so you can see it. Talk soon, guys.